Hello, statistics people. This is the first part of your Thursday pre-recorded lecture. We're going to take a look at just refreshing our memories on linear functions and models for linear functions. I'm hoping this will be a little bit of a review, and for those of you that maybe haven't seen linear functions in a little while, just helpful with regards to some of the terminology and how to do a little bit of the algebraic work with linear functions, because that's going to be the main focus of our study here till probably close to reading week. So a linear function is any function that has the form mx plus b. So you've probably heard that beaten to death at high school. M here is called the slope of your line and b is called the y-intercept. So we'll talk about how to calculate the slope and what that means for the line. And then the idea here with the intercept is that b tells us exactly where this line is going to cross the y-axis. Now in our course, I will use x and y loosely to refer to the axes, so the x and y axes, but just be mindful that usually what we're going to be doing is having a scatter plot in which along the x-axis is going to be our independent variable, or explanatory variable is how we've been calling it. So this is the variable that the researchers will be potentially doing some alterations of to see how it affects the dependent variable, which is our y variable, and we've been usually calling that the response. Okay, so it's probably more likely that you'll hear me say the explanatory and the response variable while talking about the x and the y axes. Now, when it comes to slope, we have really just kind of two major terms that go along with slope in our course. We're going to either be talking about a positive kind of slope or a negative kind of slope. And it really just is about the overall slant or the relationship that we have between our variables. So if x and y have a positive kind of relationship or association, we might say that the line of best fit has a positive slope. So this is all right, sorry about that, guys. We had a little afternoon visitor here at your statistics prof's residence. After I shooed them away, let's start talking about slope again. So the main two kinds of relationships are that positive kind of a relationship or association where we have a slant upwards and to the right. This would indicate usually that we have a positive number in front of that x value. So I'm working with something like y equals positive number plus some intercept number. So that would be an example of a line with a positive slope. It's also possible when we go to make our line of best fit, we could get a negative number in front of the x. So in this case, this is a line that's going to be slanting downwards and to the right. So something like y equals negative number in front of the x plus some intercept number. So those are a couple examples of positive versus negative slopes, and they just have, the slope just has an overall connection to essentially how steep that slant is going to be with regards to our line of best fit. Now, if you happen to know a couple points on the line, you could calculate the slope using the difference in the y's divided by the difference in the x's. So some of you might know this as the rise over run formula. So we typically call this distance here the rise, so the difference between y1 and y2, so the change in elevation essentially between the 2 points here and here. And then we call the change in the x values the run. So this is the change in the horizontal direction. So it's just a really nice formula. If you happen to know a couple points and you did want to calculate the slope by hand, this is the easiest way to do it. So let's take a look at a couple examples of how to do that. So there's two slopes we want to calculate in this particular example. So we're first going to calculate the slope passing through the 2 points. And then we'll take a look at an actual graphical example. Try to isolate a couple points on here and calculate the slope. So for part 1, I have 2 points here already. So it's a matter of using the y2 minus y1 over x2 minus x1 formula. And I'm just going to come back to our 2 points here and label them as well. So let's call this x1, y1 and x2, y2. Now I can make a substitution into my formula. We have y2 is negative 1, y1 is 5, x2 is 5, and x1 is 2. So just simplifying this, we get negative 6 x over 3 for a slope of -2. Okay, notice here that the order doesn't matter if I had swapped the names to x2, y2 to talk about 2, 5, and x1, y1 to talk about 5, -1, and I went through the procedure, I still should get the same slope of -2. So that's one nice thing about, it doesn't really matter how I choose these points, I should always come out with the same slope number. Okay, now shifting our attention over to this second line. In my notes, I went and calculated a couple points here. So it looks kind of like the line's going to pass through maybe these 2 points here. And so we're going to try to label those points so that we can use the rise over run formula. So this point up here has an x value or an x coordinate of 0. It has no movement to the left or the right. And it's gone up 1, 2, 3, 4 units. Okay, so I can see that kind of movement up 1, 2, 3, 4 in the y direction, but no movement in the right or left direction from the origin point, which is right here. And for our other point, we're going to have a movement of 1 to the left, and then we're going to go 1, 2 upwards. So this point should be -1, 2. And once again, for this second one, let's go ahead and set up our y2 minus y1 formula. And maybe I'll take 0 and 4 as y2 and x2. And we'll take 2 and -1. Just being a little careful here about how we substitute in that -1. It needs to be subtract -1. So my denominator is going to become 0 plus 1. So I'm going to get 2 over 1, or just 2 here, for this particular slope. So realistically, probably not something we're going to be doing that much in our course, but I mean helpful if it's something that you do need to do by hand. Most of the time, to get these slope numbers, Microsoft Excel or our calculator has a really good capacity to be able to do that for us with the data that we supply it. The other kind of major piece to a linear function is the y-intercept. So we might be interested also in determining how to calculate the y-intercept. And in general, the intercept method basically says whatever intercept you'd like to calculate, whether or not it's the x or the y, you're going to set the opposite variable equal to 0 and solve for the one that you're interested in. So for example, if I'm interested in finding the y-intercept, I'm going to substitute x equals to 0 because at the y-intercept there's no movement in the x direction, and that will allow me to solve for y and get an ordered pair that will let me talk about that intercept. The same is true if I would like to find the x-intercept. So if I'm curious about where y is equal to 0, where there's no movement up or downwards on this line, I could do that, and then I could solve for x and get something called the x-intercept. So I'm going to show you just quickly how to do that algebraically. So supposing that we have the following form here, y equals -4x plus 8. If we want to find the y-intercept, we're going to set x equals to 0. And we get y equals -4 times 0 plus 8. And we get y is equal to 8, because -4 times 0, of course, is 0. So we could say that 8 is equal to the x-intercept here, or we could write it as an ordered pair. So as a pair, we know that the x-coordinate must be 0 and the y-coordinate must be 8. So hopefully that's kind of an obvious answer, because this number here represents our slope. This number here is our y-intercept number, b. So it should come out to be the solution to the y-intercept problem if we use the x equals 0 kind of method here. The other one, finding the x-intercept, is usually a little bit more challenging because you set y equals to 0, and then you have to do a little bit of algebraic rearrangement here to get the x-intercept. So for the x-intercept, let's set y is equal to 0 so that we get something that looks like this. I'm going to subtract 8 from both sides and then divide both sides by -4. So -8 divided by -4 is +2. So in this case, we could say that 2 is the x-intercept, or as an ordered pair, if we wanted to see that, 2 would come first because that's our x-coordinate, and we've set y equal to 0. And really the advantage of this intercept method is that it does allow you to plot that line fairly quickly if you needed to plot that line by hand. So immediately I now have 2 points. I can plot those 2 points on the XY plane, connect those with a nice straight line, and bada boom, there's my line negative 4x plus 8. So that's the real advantage of the intercept method. But like I said, realistically, we're more likely going to be working with scatter plots, so something that looks like this. And we're going to be interested in whether or not we can create some kind of linear model based on the data that we have. So it's less likely that we're going to be going through the intercept method to do stuff, and that's just life. So here, maybe we've collected some information on protein content and fat content of specific things, and we're curious about whether or not there is an association or a relationship between the amount of protein in, I don't know, like a burger versus the amount of fat that's in that burger in grams. And it clearly kind of looks like there's a bit of a linear relationship here. Like I could kind of roughly kind of plot in where I think the line of best fit might be. Of course, using Microsoft Excel would be able to put that in there for us a little bit clearer. But that's more likely how we're going to be using our linear relationships, is trying to figure out how to model using this data and then how to extrapolate using this data. So here, protein, of course, is the explanatory variable and fat is the responsive variable, if that's something that you wanted to just jot down into your notes. So our explanatory variable always will be along the x-axis, and we're going to be thinking about our responses always along the y-axis. And if it looks like there might be a linear relationship between the data, which according to that last plot kind of looks like there might be, we could use what's known as a linear model. And a linear model usually comes in the form y equals bx plus a. And I've written it down specifically like this because this is how our calculator is going to do the work for us. So as we go to use our calculator to find these slope numbers or find the intercept numbers, these are the capital letters that the calculator uses. Usually there's like a little hat here over top of the y, because I guess y likes to have a party if there's a linear relationship. But there's a little accent here just to let the reader know that this is a model based on the data. So in other words, we don't use y by itself. We usually will use y with a small hat over top of it, just to let the reader know that we've made a line of best fit. So that's really all this accent means. And of course, underneath here, just explaining to you that capital B is now we're going to use capital B more often to represent the slope of our model, and we're going to use capital A to represent the y-intercept of our model. And so let's say we went ahead and we calculated the slope and the intercept, let's say using Microsoft Excel, and we get this beautiful kind of linear model here that we can put over top of our scatter plot. The idea with a linear model is, we want to use this to try to be predictive about some of the information that we have. So for example, using the linear model, if I actually had one, I might be able to make a prediction about how much fat I would expect to see if a particular burger had 60 grams of protein. So for instance, I might expect the fat level in this burger to be about 80 grams if I see about 60 grams of protein. This is the whole point of the linear model, the ability to make extrapolation to a certain extent, and to be able to kind of, like I said, kind of make some guesses for future data or for current data. And so that's what this slide here is just trying to explain. This is the real advantage, the real reason why we want to use some kind of best fit model, because if it explains the data very, very well, then it allows us to actually make some of this extrapolation happen. However, you just have to be really careful about how far you extrapolate. So you have to kind of be mindful about, if we go back to the burger example, like, does it really make sense for a burger to have like 300 grams of protein? Probably not. So I probably don't want to extrapolate that far using my linear model, but making educated guesses based on the model for smaller grams of protein in this burger kind of makes sense, especially if they're between like 15 to 45. A lot of our data kind of lies between, I would say, 0 to 45. So if I extrapolate inside of that region, it's certainly, I don't think that's an unreasonable thing to do. But, extrapolating for 300 might be a little unreasonable because we're not living in America. We're not going to be eating a burger that big. And this is, I think, really illustrated by the following comic, and I will let you take a little read at that. So, of course, the humor here is that we're trying to extrapolate that we're taking our two data points, right? Yesterday we had no husbands. Today we have one, and then by the end of next month we're going to have over 4 dozen. So you better start getting better wedding rates. Of course, we can't get married right now for COVID anyway. But yeah, so I mean, there's an extent to how far you can extrapolate in a way that makes sense. So let's just work through one final example here. And I'm just going to exit out of here, and we'll just copy and paste this into a place where I can do a little bit of work for you. And there should be a blank page for you guys so you can follow along and just jot down some of the... Yeah, so I think the last page here is a blank page for you, so you can just follow along and copy down some stuff on that last page. So let's say we've gone through Microsoft Excel, we've found a linear model that seems to fit the data quite well, and it's going to predict total revenue earned in dollars by considering the number of ticket sales. So here the number of ticket sales is the X variable, it's the explanatory variable, and our response variable is the Y variable, which is our revenue earned. Okay? So the first question here asks us, what kind of information does the y-intercept tell us? And what kind of information does the slope tell us? Okay, so let's break this down. So in this particular instance, our y-intercept is here. So in this particular case, we might think of the y-intercept as the amount of money that we would need to pay back, or the amount of money that we borrowed in order to host this event. So if I don't sell any tickets, in other words, if X is equal to 0, I still owe $14,228. So my revenue is essentially a negative dollar amount. So that's how I might interpret the y-intercept, as like a dollar amount owing if I don't sell any tickets. And let's take a little peek at this slope number as well. So if X represents the number of tickets sold, what I need to do in order to get the revenue is actually multiply the number of tickets that I sell by some kind of price amount. So this 36.87 is going to represent the amount of money that I earn per ticket sale. Okay, or you might even think about this as like the cost price of the ticket, right? So this is the amount of money that's going to come into our pockets every time somebody purchases a ticket. Okay, so second question. Let's call this so we answered question A. Let's move into question B. So roughly how many tickets do we need to sell in order to break even? So in other words, how many tickets do I need to sell in order for my net revenue to be 0, or for us to pay back this $14,228. So to break even, gives us the following relationship. It means I want to figure out how many tickets I need to sell in order to pay back that original debt of $14,228 that I owe. If we take this number, 14,228, and divide by 3687, we get that X is equal to 385 point, let's say 9. Okay, and remember X represents the number of tickets that we sell. So in this instance, we're going to need to sell about 386 tickets in order for us to break even and not run a deficit. I tried so hard to save that 8, but failed miserably. Okay, so around 386 tickets, I would expect really not to see that much of a profit on this particular show. But as soon as I start to sell more than 386, now I'm going to start to see revenue coming in. Right? I'm going to start to have cash left over in my pocket. But up until 386, we're kind of running at a deficit, essentially. Okay, part C, we're going to do a little bit of extrapolation. We're going to use our model here to try to predict the total revenue of selling 1,000 tickets. And then we're going to try to predict the total revenue of selling 20,000 tickets. So this is representing an X value. So let's say X is equal to 1,000. What am I going to get for total revenue if X is equal to 1,000? Well, let's toss that into our calculator. So 3687 times 1,000 minus 14,228. So I get about $22,642. Now remember, this is something you can do in Microsoft Excel if you have your data, like the full data set, using the forecast.linear command. So we're just doing it by hand in this particular instance because I already have my model and I can just sub X into that model and get a pretty good idea of what that answer should be. Okay, that's pretty good revenue, right? Like to get a revenue of about $22,000, I'd be happy with that if I was hosting an event, if I was allowed to host an event. And finally, let's take a look at what happens if we sub in 20,000. So let's take our 3687, multiply by 20,000, and see what kind of revenue we get in this case. Ooh, that's nice. So we get about 723,172. That's a pretty good revenue as well. And of course, the last question here is taking a look at these two extrapolations, these two predictions, and trying to figure out which one makes more sense. Now, I mean, there definitely are places that could sell 20,000 tickets. Totally a reasonable thing. However, I feel like those places that have that kind of capacity are probably not going to sell a ticket at $36.87. I think we're probably more realistically in the range of like in a couple thousand seat theater. Each ticket's about $40. So I think the first prediction kind of makes sense based on the information that we have. Although, like I said, it's not unreasonable to have a place that has 20,000 seats, but you're likely to see, I think, the average ticket price be much higher than $40. So I would say that the prediction with 1,000 tickets is probably a bit more reasonable based on the information, and maybe the 20,000 ticket sales is pushing it a little bit, especially for a place like Penticton, right? If this is representing a place in Penticton, probably don't really have a place that can hold 20,000 people. So hopefully that makes sense. And like I said, that's the first part of our lesson for Thursday. We're going to move into the more on linear regression stuff next.